If you let your instrument currency lapse and you do not fly the required approaches, holding, intercepting, and tracking under the hood with a safety pilot or in an approved flight simulator or flight training device within the following 6 calendar months, then you must take an instrument proficiency check to regain instrument currency. These are given by instrument flight instructors and examiners. The tasks required on an IPC are spelled out in the Instrument Rating Practical Test Standards book and include most of the areas of operation from the instrument flight test. Again, the IPC must be accomplished in the appropriate category aircraft or in a flight simulator or flight training device that is representative of the category for which the instrument privileges are sought. Successful completion of the proficiency check makes the pilot current for 6 calendar months. It makes sense that a pilot who has not logged instrument time or flown on instruments for a while should be looked at by someone more qualified than a safety pilot. Safety pilots must be appropriately rated. This means at least a private pilot with a category and class rating for the aircraft flown. The safety pilot doesn't need an instrument rating, but does need a current medical. For simulated instrument flight time, the airplane must have fully functioning dual controls. FAR 91.109 does provide for exceptions for single-engine airplanes equipped with a single throw-over control wheel. Instrument flight time logbook entries must include the place and type of approach made, and for simulated instrument time, the name of the safety pilot. Pilots should remember that it's not unusual to be out of radar contact when flying at low altitudes or when distant from radar antennas. Non-radar longitudinal and lateral separation is complex and based on the true airspeed of the aircraft being separated. For airplanes at the same altitude in the same direction, required separation can be as much as 10 minutes. The time can be decreased if the lead aircraft is faster or if either or both aircraft have DME or RNAV. Non-radar altitude changes can require as much as 10 minutes separation to climb or descend an aircraft through the cruise altitude of another aircraft. When you're out of radar coverage, pilots of IFR aircraft are expected to make position reports. Pilots on IFR flights will also have to make position reports when there is a center or approach radar outage. The volume of traffic handled will be drastically reduced and there will be lengthy delays and diversions to other airports. Without radar, the controller has to rely on these position reports and estimates made by the pilot at compulsory reporting points. Both Jeppesen and FAA charts show compulsory reporting points as solid triangles. In the days before radar, the instrument charts had a lot more solid triangles. If you are not flying on an airway, the fixes used to define the route become compulsory reporting points. We still have compulsory reporting points because radar outages, while fairly rare, do happen. The words radar contact lost or radar service terminated let you know you will need to make position reports. The words radar contact tell you position reports are not necessary. Let's look at a position report. If you remember that the controller cannot see the position of the airplane, the format of the position report makes good sense. As always, the controller wants to know who you are. Next is the name of the reporting point. The next item is the time the airplane was over the reporting point. This is necessary because pilots sometimes have to wait several minutes to get on the frequency. Time over the reporting point is followed by the altitude. Without radar, there is no Mode C, and the controller wants a verification of the airplane's altitude. The type of flight plan is omitted when reporting to approach controls or centers. To enable the controller to plan for possible conflicts, the next item is the estimated time over the next compulsory reporting point, and last, as a running check, the name of the reporting point after the one for which the estimate was made. If any item of communications, navigational, or approach equipment becomes inoperative, the controller should be told. In this report, the pilot should tell the controller the degree of impairment and the nature of any assistance desired from air traffic control. There are some required IFR communications. We must report when encountering all hazardous weather and any unforecast weather conditions. We also have to call with any other information relating to the safety of flight. If any of the avionics malfunction, we have to call. If you deviate from your clearance, for example to avoid traffic or other emergency, you must inform ATC as soon as possible. Additionally, pilots operating IFR are to call when vacating an altitude for a newly assigned altitude. If an altitude change is to be made when you are flying VFR on top, a report is required. You must tell ATC when you can't maintain 500 feet per minute in a climb or descent, or when the speed varies from your flight plan speed by 5% or 10 knots, whichever is greater. If cleared to a hold, a report should be made giving the time and altitude when reaching the holding fix. Likewise, a report should be made when leaving a holding fix. If you miss an instrument approach, you should report this and include your request for action desired. The reports just outlined are given whether or not the aircraft is in radar contact. When not in radar contact, the following reports are added to the list. We have to report the time and altitude of passing each designated reporting point. If you are going to miss an estimated time over a designated reporting point by more than 3 minutes, that calls for a report. You must report leaving the final approach fix inbound on a non-precision approach, or the outer marker or other fix used in lieu of the outer marker inbound on a precision approach.
The transponder is a simple device to use. All we have to do is set in the number which is assigned by ATC for identification purposes. For example, the ATC computer recognizes code 0435 as Cirrus 294 Charlie Golf. If the aircraft is equipped with altitude reporting mode C, the transponder function switch should be set on the altitude position. When interrogated by ground radar, the transponder reply will be known to the computer and it will tag the target on the radar scope as November 294 Charlie Golf. Further, if the aircraft is equipped with mode C, as virtually all aircraft used for IFR are, the data block on the scope will also show the pressure altitude of the aircraft. Impressive, but not new technology. Transponders were used under the name IFF for identification friend or foe in World War II. If the transponder didn't give the right answer, you were literally under the gun. Some colorful language from those days carries on today. The IFF, or transponder, was known as a parrot, thus the current squawk terminology. When they wanted the transponder off, word was to strangle the parrot. The transponder has an ident feature. When the controller says squawk ident, and we do, it identifies the target on the scope. Before the current radar system with discrete codes and data blocks, all the controllers had were targets, and positive radar identification was always made with a squawk ident. It is still used sometimes when a controller wants a double check on the identification of a radar target or when there are computer problems. There's a little light on the transponder that blinks whenever the transponder is interrogated. Occasionally this can cause some confusion. When a controller calls with word that radar contact is lost and you see the light still blinking, you may wonder why radar contact has been lost. There are two possibilities. There are radar ground stations all over the country serving military as well as civilian needs. You may be in a position where the radar used by the controller you're talking with can't see your transponder. Other ground radar systems interrogating your transponder may account for the continued blinking of the light. Another possibility is that your transponder is replying to an aircraft equipped with a traffic alert and collision avoidance system. TCAS is installed on all airliners and most corporate aircraft, and similar devices are available for smaller general aviation aircraft. These systems actively interrogate the transponders on nearby aircraft and display the relative position and altitude of traffic. The most sophisticated versions will command and coordinate evasive maneuvers to avoid conflicts. The newest transponders are called Mode S and feature data link capability as well as altitude reporting. These can utilize the Traffic Information Service uplinked by many FAA radars. TIS shows nearby traffic on a multifunction display or overlaid on some moving map GPS screens. If you don't have a working transponder, none of these traffic avoidance systems will see your aircraft. Transponders with Mode C are required inside Class A, B, and C airspace, as well as within 30 nautical miles of Class B and the space above all Class C areas. The equipment is also required at or above 10,000 feet MSL, excluding the airspace within 2,500 feet above ground level. If the transponder fails, ATC may, if requested, allow you to continue to your destination even if you're in airspace that requires Mode C. If a transponder is installed, it is required that it be on whenever the airplane is operated in controlled airspace, which is everything except Class G. Transponders and Mode C altitude reporting equipment must have been tested by a certified repair station within the preceding 24 calendar months. It is against the regulations to operate IFR in controlled airspace above the maximum altitude at which all installed altimeters as well as the automatic altitude reporting equipment have been tested.
The FAA is very specific about the requirements for an alternate airport on an IFR flight.
In the rule about required fuel, it states that, considering weather reports and forecasts, you must have enough fuel to fly to the first airport of intended landing, fly from that airport to the alternate airport, and fly after that for 45 minutes at normal cruising speed. The requirement for an alternate airport is waived for a destination ceiling of at least 2,000 feet and a visibility of at least 3 miles. Anticipation of this condition is based on weather reports or forecasts or both, and must exist for at least 1 hour before and 1 hour after the estimated time of arrival. The airport must have an instrument approach procedure. Further, the rules require that to be used as an alternate, an airport must have a forecast of conditions equal to or better than the alternate minimums listed for the airport. If no alternate minimums are specified, the basic requirement is for a ceiling of 600 feet and a visibility of 2 statute miles if the airport has a precision approach, or an 800-foot ceiling and 2 miles visibility if there is a non-precision approach. GPS WAAS approaches have a glide slope, but they are not considered to be precision approaches. So for flight planning, you must use the non-precision alternate minimums of 800 feet and 2 miles unless specified otherwise. If your GPS is not WAAS certified, the alternate airport must have an approved instrument approach procedure other than GPS that is anticipated to be operational and available at the ETA and which the aircraft is equipped to fly. If an airport has no instrument approach, it can be used as an alternate if conditions are forecast to be such that the approach and landing can be made in basic VFR conditions from the minimum en route altitude. In many cases, an airport without an approach would not be covered by a terminal aerodrome forecast, so the area forecast covering the airport would be used instead. Picking an alternate can be tricky business because weather forecasters are not sympathetic to the alternate needs of IFR pilots. They will often forecast acceptable conditions, but then include temporarily or a probability of weather conditions which don't meet the minimum alternate criteria.
Life is a compromise. Those who fly high have to learn additional rules and procedures. For instance, in Class A airspace, which starts at 18,000 feet MSL and extends up to and includes flight level 600, all aircraft must fly under instrument flight rules. Class A is presently the only operational airspace that requires all aircraft to be on an IFR flight plan regardless of the weather conditions. Naturally, the pilot must have a current instrument rating to file the IFR flight plan. The letters VFR are not used in Class A. For instance, VFR on top is not allowed. Even though on an instrument flight plan, however, you, the pilot, are still responsible for see and avoid separation anytime you're operating in visual meteorological conditions. This includes when in Class A airspace. The importance of this is brought home by the fact that at just a 360 knot rate of closure, an aircraft 3 miles away will be on you in about 15 seconds. ATC will still be providing radar traffic advisories, obviously, but it's still your responsibility for visual separation. All aircraft must be at assigned flight levels. The aircraft in Class A must be equipped with a radio providing direct pilot-controller communication on frequencies specified by ATC. This translates to requiring a 720-channel transceiver. Naturally, a transponder and Mode C capability are required. If the transponder fails while in Class A, ATC may, if requested, immediately approve the flight to continue to the destination using Class A airspace. Checklists usually call for setting the altimeter to 29.92 inches of mercury, climbing through 17,500 feet. ATC requires the controller to furnish the current altimeter setting when clearing an aircraft to descend below flight level 180. To maintain at least 1,000 feet of vertical separation, the lowest usable flight level is moved up when the altimeter setting falls below 29.92. For example, when the altimeter setting is between 29.42 and 29.91, the lowest usable flight level listed on the regulations is 185. As a practical matter, flight level 185 would not be used, making flight level 190 the lowest assignable flight level. Not specifically a part of Class A rules is the requirement for DME at and above 24,000 feet MSL if you are navigating by VOR or VOR-based area navigation equipment. This dates back to the days of incomplete or no radar coverage. Remember the non-radar separation standards discussed in Volume 2? Non-radar separation is easier and requires less space between aircraft if both aircraft have DME or an approved GPS-based area navigation system. Loss of distance measuring capability requires a report to ATC. However, ATC won't banish you to levels below 24,000 feet if the DME fails.
In addition to the instruments and equipment for day or night VFR, there are specific instruments and equipment required for IFR. These are listed in the regulatory language of FAR 91. Here's a quick look at the regulatory language. You are required to have two-way communication and navigation suitable for the route to be flown. That's rather general, but the FAA gets specific when operating IFR in Class B airspace. There, you must have a working VOR or TACAN or an operable and suitable area navigation system, such as an IFR-approved GPS. A gyroscopic rate of turn indicator is required except for some aircraft and helicopters which have a third attitude instrument system. An exception to this rule is that light airplanes operated under Part 91 may substitute a second attitude indicator for the turn coordinator. What they call a slip skid indicator, most of us call the ball. A sensitive altimeter, which means an altimeter adjustable for changes in barometric pressure. A clock which displays hours, minutes, and seconds with a sweep second pointer or digital display. There must be a generator or alternator of adequate capacity. Finishing the gyro instruments are a gyroscopic pitch and bank indicator and a gyroscopic direction indicator or equivalent. We call them the attitude and heading indicators. A VOR receiver used under IFR must have been operationally checked and found to be within limits within the preceding 30 days. The common ways of checking a VOR receiver are the Very High Frequency Omni Test, or VOT, Designated Surface Checkpoint, Designated Airborne Checkpoint, and the Dual VOR Receiver Check. VOTs and surface and airborne checkpoints are listed in the Airport Facility Directory. A VOT is a station that transmits the 360-degree radial in all directions. Regardless of geographic position, you are always electronically north of a VOT. Thus, the CDI should center on 360 with a from indication or 180 with a to indication. A radiomagnetic indicator, RMI, has a compass card which is actuated by the aircraft's compass system. The heading is shown under the index at the top. This RMI shows a heading of 20 degrees. The RMI has two course to the station pointers, which can be switched to be used with either a VOR or an ADF receiver. The thin number 1 pointer is receiving information from an ADF receiver. The wide or number 2 pointer is receiving VOR information. The course to the VOR station is 300 degrees. The course to the non-directional beacon is 25 degrees. The tails of the needles indicate the radials. The airplane is at the intersection of the 120-degree radial of the VOR and the 205-degree bearing from the non-directional beacon. When the receiver is tuned to a VOT, the RMI needle for that receiver should point within plus or minus 4 degrees of 180 degrees, which is always the course to a VOT. Some VOTs can be used on the ground or in flight. Others can only be used on the ground. On the surface and in flight, the tolerances are plus or minus 4 degrees of 180 degrees to and 360 degrees from indications. Designated surface checkpoints are places on an airport. On taxiway A4 on the run-up area for runway 14, the airplane is on the 328-degree radial of the Muncie VOR. To use the checkpoint, position the airplane on the designated spot. Tune in the VOR, and the CDI should center within 4 degrees of 328 degrees with a from indication, or 148 degrees with a to indication. In the vicinity of Muncie, you will be on the 180-degree radial and 8 miles from the VOR DME when over the highway and railroad intersection. Note that this check specifies an altitude of 2,500 feet. The tolerance for this designated airborne check is plus or minus 6 degrees of 180 with a from indication, or 360 and a to indication. Airborne checks made over a designated checkpoint are the only VOR receiver checks that have a tolerance of plus or minus 6 degrees. The rule does set an order of preference in stating that if a VOT is not available, a designated surface checkpoint should be used, and if a designated surface checkpoint is not available, use a designated airborne checkpoint. The dual VOR receiver check is in a separate paragraph and is not subject to the order of preference. The two VOR receivers must be independent except for the antenna. They can be checked on the ground or in the air. It is not necessary to be on or over a designated checkpoint. You only need to receive a VOR signal. Tune the two receivers to the same station and center the CDIs to the course to the station. The maximum difference allowed is 4 degrees between the two indicated bearings to the station. The dual VOR receiver check specifies that the indicated bearing to the station must be used. There are two other checks which can be used. One is a test signal radiated by a certificated and appropriately rated repair station. The tolerance allowed is within 4 degrees of the radiated signal.
The catch is that the repair station certificate holder or representative must make an entry in the aircraft records certifying the bearing transmitted for the check and the date of the transmission.
The other check which can be used in flight if no other check signal or point is available is the homemade airborne checkpoint. Start with a VOR radial that is the center line of a Victor airway and pick a prominent point that is on that radial. Preferably, the point should be more than 20 miles from the VOR. Like the designated airborne checkpoint, the CDI should center within 6 degrees of the radial. Remember that 6 degrees is the allowable tolerance only for VOR checks made when airborne over a checkpoint. All other receiver checks, including the VOT and dual receiver checks in the air, must have a tolerance of 4 degrees. The VOR check must be entered in the aircraft log or other record. The entry must include the date, place where the check was made, the error observed, and the signature of the person who made the check. I like the acronym PADS. P-A-D-S, P for place, A for amount of bearing error, D for date, and S for signature. The pilot in command is responsible to determine that the aircraft is airworthy. An aircraft may not be airworthy if the required checks and inspections have not been completed. Starting with the one most frequent, the VOR operational check is required only for IFR. The annual inspection of the aircraft is required for VFR or IFR and must have been completed in the preceding 12 calendar months. In order to use a transponder, for VFR or IFR, it must have been checked within the preceding 24 calendar months. Finally, for IFR in controlled airspace, the altimeter, including the encoder and static pressure system, must have been checked in the preceding 24 calendar months. All the inspections and checks must be recorded and current. The certificates and documents required for VFR are also needed for IFR operations. If you still have a paper pilot certificate, you'll need to get a new plastic replacement in order to fly after March 31st, 2010. Student pilot and temporary certificates are exempt from the plastic requirement. New plastic certificates also have the endorsement English Proficient, which is an ICAO requirement for international flying. The FAA began adding the English Proficient endorsement in 2008. If your pilot certificate was issued before then and you intend to fly internationally, you'll need a new certificate. If emergency authority is used to deviate from an ATC clearance, the pilot shall notify ATC as soon as possible and request an amended clearance. In checking weather for VFR flights, we put a lot of effort into making sure that the ceiling and visibility will allow visual flight to the destination. Flying visually means that, as we fly along, we can see what is going on. Checking weather for an IFR flight takes on another dimension. We might be flying in the clouds. We have to learn something about the nature of those clouds. Icing in the clouds and turbulence and thunderstorms take on new meaning. Visibility and ceiling are important too, especially at the destination and the alternate. We can't ignore the visibility and ceiling en route either, because it is always necessary to know what the options are as we fly along, in case the best course of action becomes a landing short of the destination. With the advent of DUOT and other computer weather briefing systems, a lot of pilots are flying away with 5 to 7 pages of weather information. In the good old days, we flew with a page of notes or less on the weather. We still do this when a computer is not available. This probably leads you to wonder what you really need before flying away IFR. The most basic necessity is a knowledge of the synopsis. Where are the highs, the lows, and the fronts? For a lot of us, the first glimpse of this comes from a morning TV show. While many of the people who present this information are actors and not real meteorologists, the information is from those in the know. But there is one caveat. Some show the current map. Others show a map that covers what conditions are expected to average during the day. If it shows rain, but the sun is shining, it'll probably rain before the sun sets. The aviation weather products most often accessed by computer or that are used by the briefer we talk to on the phone are the area, aerodrome, and winds aloft forecasts. METARs, PIREPs, radar, airmets, and SIGMETs, and especially convective SIGMETs on thunderstorms. These tell us what we need to know before flying. You may have heard some pilots grumble about forecasts. They're too negative, or they are seldom correct. Forecasts, though, are based largely on computer models of the atmosphere, and it is important that we know what is anticipated. If the forecast does turn out to be incorrect, then we have to start the information gathering process anew. One of the first things to look at is the synopsis section of the area forecast. This is all-encompassing and usually waves flags about possible inclement conditions. Remember, though, this is only a general summary, telling you where to be wary of active weather systems and their associated conditions covering the entire forecast period. Radar is useful in telling us where rain is falling and where thunderstorms are located. Some weather services will show the echo tops, speed and direction of movement, and additional information, including storm watch boxes and areas of particularly dangerous weather. Remember, though, that NEXRAD images are history and conditions do change. SIGMETs, especially convective SIGMETs, are both statements telling of a significant weather condition and outlooks on how that condition is expected to develop. Never fly away without checking for SIGMETs. While they are billed as in-flight weather advisories, they are quite useful right before takeoff in defining areas where trespassing will not be forgiven. The convective outlooks are national thunderstorm forecasts issued by the Storm Prediction Center in Norman, Oklahoma. These forecasts outline areas in the continental United States where severe thunderstorms may develop. The Day 1 and 2 outlooks also forecast areas with a 10% or greater chance of general activity. General thunderstorms are forecast to the right of the unlabeled lines. Severe thunderstorms are possible to the right of the other lines, and the risk of severe weather is labeled slight, moderate, or high. These labels do not describe the thunderstorms themselves. For example, an area with a slight risk does not mean that the thunderstorms will be slightly severe, rather that the severe thunderstorms are expected in small numbers and/or low coverage. Places marked C text are also expected to have severe weather, but with less chance or lower coverage than the slight risk areas. In addition to the chart, a convective outlook includes a technical discussion describing the factors expected to produce the severe weather. This section is for meteorologists to help in their forecasts and may contain weather terms unfamiliar to pilots. Each area with a risk of severe thunderstorms will have its own forecast discussion. General thunderstorm discussions might not be included if severe thunderstorms are predicted. The Day 1 convective outlook covers the first 24-hour period. The Day 2 outlook covers the second 24 hours, and the Day 3 outlook covers the 24-hour period after that. A Day 4 through 8 outlook covers the following 5 days. The Day 1 outlook is issued 5 times daily, and each issuance is valid until 12 Zulu the following day. The Day 2 outlook is issued twice daily and covers the period from 12Z the following day to 12Z the day after that. Both forecast and observed winds aloft charts are available. In addition to wind speed in knots, the temperature is plotted in degrees Celsius on most of the charts. Wind direction to the nearest 10 degrees and speed are indicated by arrows with pennants and barbs. The first digit of the wind direction is omitted, and the second digit of the direction is shown at the tail of the arrow. The first digit, a 0, 1, 2, or 3, is determined by the general direction the arrow is coming from. This arrow is coming from a direction between 0 and 90 degrees. This arrow is coming from a direction between 180 and 270 degrees. The number at the tail is the second digit of the direction. This arrow is from 050 degrees and this one from 240 degrees. To determine speed, add the barbs and pennants. A half barb is 5 knots, a full barb 10 knots, and a pennant is 50 knots. The number next to the station circle is the temperature in degrees Celsius. Putting it all together, the wind observed at this station was from 230 degrees at 35 knots, and the temperature was minus 47 degrees Celsius. Low-level significant weather prog charts deal with forecast weather from the surface to 24,000 feet. They predict the positions and characteristics of fronts, pressure systems, and precipitation using these standard weather symbols. The symbols are graphically suggestive. For example, the hurricane symbol is a solid circle with 2 swirling lines. The high-level significant weather prog charts forecast weather between 24,000 feet and 60,000 feet.
The air traffic control system is responsible for control of aircraft on IFR flight plans within controlled airspace.
When you are changing altitude, the controllers expect you to climb or descend at an optimum rate consistent with the airplane's operating characteristics. Maintain this rate until within 1,000 feet of the new assigned altitude, then at 500 to 1,500 feet per minute. This allows more efficient climbs and descents by high-performance aircraft. ATS route, or Air Traffic Services route, is a generic term which includes the 4 different sets of airways in the United States, as well as arrival and departure routes. Victor Airways go from 1,200 feet AGL up to, but not including 18,000 feet MSL. Practically, the highest assigned altitude available on Victor Airways is 17,000 feet. Victor Airways are also referred to as VOR Federal Airways. High-altitude airways, called jet routes, start at 18,000 feet MSL and extend up to and include flight level 450. Aircraft above flight level 450 navigate by point-to-point or direct navigation. Published RNAV routes are found on both the high and low altitude charts. They are painted in blue with magnetic reference bearings. Q routes are found on the high altitude charts. T routes are low-altitude RNAV routes, generally established for transition around busy terminal airspace. T routes have also been created as supplements to existing ATS routes and as replacements for other ATS routes when underlying nav aids have been decommissioned. Finally, there are still colored airways in use in coastal North Carolina and Alaska based on low-medium frequency nav aids. Low-medium frequency airways are named for one of 4 colors: red, green, amber, or blue, and given a number. Airways are 8 nautical miles wide, 4 either side of the center line. The airspace is protected, and obstacle clearance, 1,000 feet in non-mountainous areas and 2,000 feet in designated mountainous areas, is assured within the confines of the airway. Low altitude and route charts provide navigation information for IFR flights on Victor Airways and RNAV routes. Scales vary from 1 inch equals 7 miles to 1 inch equals 31 miles. The FAA issues a new set of en route charts every 56 days. Each chart has a complete legend on the inside fold. Below the unfold arrows, we find that panels Alpha through Echo are on the L11 and panels Foxtrot through Juliet on the L12. 1 or more panels have an alphabetical listing of the airports on the chart. Next to each name is the FAA identifier for that airport. Beside the ID is a letter that tells us the panel on which the airport can be found. There is no airway between Geneseo and Ithaca. An IFR flight between these vortexes is called a direct flight. In IFR speak, direct is a route which is not on airways. For a direct flight, the pilot must refer to the off-route obstruction clearance altitude called the OROCA. The OROCA provides the same obstacle clearance as a MOCA, but does not guarantee nav signal reception, radar coverage, or communications with ATC.
There's no one scan that works for all pilots. Proficient instrument pilots scan all the instruments, with the attitude indicator getting up to 2/3 of the scan time. As your instrument experience and capabilities increase, you'll learn what to look for, when to look for it, and the response to make.
Scan patterns in glass cockpit airplanes are similar to those used for analog instruments. The difference is where you will look for particular information. A scan advantage in a glass cockpit is that the attitude indicator can stay in sight while looking at the other instruments. A potential disadvantage is that the tape-style instruments may require more time to focus on the value being portrayed. Proficient instrument pilots in analog cockpits can determine the approximate position of the needles with a quick glance. Tape representations require you to read the value to look for changes. As you begin instrument flying, the usual tendency is to scan too rapidly, looking at the instruments without knowing exactly what you're looking for. Slow down. Get the message from an instrument before going to the next one. When the instruments become more familiar, you won't need as much time to get the message. As you gain experience, you'll learn to adjust the scan rate and sequence to suit the flight situation. There are a number of scan errors you should be aware of. The first of these is omission of an instrument or instruments. This usually happens when attitude change is made without checking the performance instruments. An example of omission is leveling off from a climb by establishing the level flight attitude on the attitude indicator without cross-checking the effect of the attitude change on the altimeter. Emphasizing one instrument is another error that is closely related to omitting an instrument. The difference is that you do not omit an instrument, but rely too much on another instrument. You can probably do a reasonable job of maintaining altitude using either the natural or artificial horizon. However, precise altitude control requires frequent checking of the altimeter. Fixation, or staring at one instrument, is also a common error. Fixation is most apt to happen as you approach an altitude during a climb or descent, or a heading during a turn. You are determined not to go through the specified altitude or heading, and thus stare at the altimeter or heading indicator while other instruments cry out for attention. If you are climbing at 500 feet per minute and have 300 feet to go, it will be about 30 seconds before you start the level off. In a standard rate turn with 45 degrees to go, it will be more than 10 seconds before the rollout should start. Typical students tend to fixate on the bank instruments more than on the pitch instruments. This is because the airplane is more stable in pitch than bank.
Before we look at straight and level and climbs and descents, let's take a quick trip around the instrument panel to group instruments in either the pitch, bank, or power column.
Starting at the top left of the T, the airspeed indicator goes into both the pitch and power columns. The attitude indicator is equally at home in the pitch and bank columns. You've probably already put the altimeter in the pitch column. Continuing clockwise, the vertical speed indicator completes the pitch instruments. The heading indicator, turn coordinator, or turn needle and the ball, or slip skid indicator complete the lineup in the bank column. To avoid confusion, we'll use the name turn indicator for both the miniature airplane of the turn coordinator and the turn needle. Power instruments are completed with the tachometer or the combination of the tachometer and manifold pressure gauge. Depending on the maneuver, each of these instruments will sometimes play the leading role and at other times may be in a supporting role. For a glass-equipped airplane, the flight and engine instruments are grouped into the same pitch, bank, and power columns. While the appearance may be different, the function is the same. Like your visual flying, most of your instrument time will be spent flying straight and level. The instrument pilot's definition of straight and level is maintaining constant altitude, heading, and for some phases of flight, a new addition, a constant airspeed. As the complete instrument pilot, you should be able to maintain heading, altitude, and airspeed at speeds ranging from cruise to approach. Within the normal speed range of an airplane, there are many combinations of power and pitch which will maintain altitude at different airspeeds. Recall, proper pitch and power produces predictable performance. For example, a low power setting and a nose-high pitch will maintain altitude at low airspeed. At the other end of the airplane's working speed range, a high power setting and low pitch attitude will bring about level flight at high airspeed. At a given power setting, the weight of the airplane can also affect the pitch attitude for level flight, but this can usually be disregarded in light training airplanes. While the attitude indicator gives us a direct picture of the pitch attitude of the airplane, let's look at the clues the indirect instruments can provide. These indirect instruments are the airspeed and vertical speed indicators and the altimeter. With a constant power setting, if there is no turbulence, any deviation from altitude is caused by a change in pitch attitude. Assuming constant power, the altimeter will give you an indirect indication of the pitch attitude. Any deviation from the assigned or desired altitude is a signal that you need to make a pitch change. The direction and rate at which the altimeter departs from the desired altitude is an indication of the amount of pitch change needed. For example, a large nose-up pitch change from level flight will show as a rapid clockwise movement of the altimeter needle. If the altimeter needle moves at a slower rate, the pitch change is smaller. These examples in a glass-equipped airplane would appear as longer or shorter trend lines on the altimeter. Any change in indicated airspeed is also an indirect indication of a pitch change. In level flight, with power constant, the indicated airspeed should remain constant. A large change in pitch attitude will result in a rapid and large change in indicated airspeed. A small pitch change will show up as a slow and small change in indicated airspeed. The vertical speed indicator displays any up or down trend of the airplane. It indirectly shows any pitch attitude deviation from level flight. Trend, or what's happening information, is displayed quickly. Rate, or how much is happening, takes several seconds to appear after the airplane has stabilized in level flight, climb, or descent. The rate delay does not occur with many glass installations. Pitch corrections for level flight should be made using the attitude indicator and limited to half, full, and 1 1/2 bar widths corrections. The pitch corrections to maintain level flight on instruments are smaller than those made using the natural horizon. When the airplane is properly trimmed, the control pressures needed for these small pitch changes are very light. A 1/2 bar width pitch change is used for altitude corrections of 100 feet or less. For corrections of more than 100 feet, use a full bar width pitch change initially, changing to a half bar width when the remaining altitude correction is less than 100 feet. The rate of return should not exceed double the altitude correction. If the error is 200 feet, the rate of return should not be more than 400 feet per minute. At this rate, it will take 30 seconds to return to the assigned altitude, giving you time to pay attention to heading, engine instruments, or navigation indicators. Try not to exceed a climb or descent of 500 feet per minute when returning to a desired altitude. Heading and bank controls are virtually the same thing. Heading will stay constant if the wings are kept level in coordinated flight. The wings of the miniature airplane and the horizon bar of the attitude indicator will give you an overall picture of the wing attitude, but small banks are difficult to detect. Small deviations from wings level attitude are more easily detected using the banking scale and center index. Odds are that bank control will require more practice than pitch control. There are several reasons for this. First, the airplane is more stable in pitch than bank, and if you're a typical VFR pilot, you refer to the altimeter more than to the heading indicator. While the attitude indicator will show if the wings are being kept level, you still need to look at the heading indicator to be sure the heading is the right one and that it is kept constant. The attitude and turn indicators are supporting bank instruments during straight flight.
The most common error for both pitch and bank control is over-controlling. Just as an excessive climb or descent will cause you to overshoot altitude, an excessive rate of turn results in overshooting the target heading.
Now let's take a look at climbs. To enter a constant airspeed climb, raise the nose to bring the miniature airplane the predetermined position above the horizon bar. As the pitch attitude is raised, increase the power to the climb setting and use right rudder to keep the airplane from turning to the left. Adjustments of the climb attitude will be dictated by the indicated airspeed. If airspeed is too high or low, the pitch attitude must be changed. Don't chase the airspeed indicator to make the change. Use the attitude indicator to make small changes of 1/2 bar width. Wait and note the effect on the airspeed indicator. As the desired altitude is approached, the level off must be started about 10% of the rate of climb before reaching the altitude. If the climb is 500 feet per minute, the pitch attitude should be smoothly changed to the level flight attitude 50 feet before reaching the final altitude. Use the attitude indicator to set the level attitude and grade this attitude using the altimeter. As airspeed approaches cruise airspeed, let's consider a concept called overpowering for power management during the level off from a climb. This technique is used to make the transition easier, quicker, and smoother. Leveling off from a climb, don't reduce power as soon as the pitch attitude is in level flight. Instead, maintain climb power until the airspeed is within 5 knots of cruise before reducing power. For a constant rate climb, increase the power to the approximate setting required for the desired rate of climb and simultaneously raise the nose to the approximate pitch attitude needed for that climb rate. As the vertical speed indicator stabilizes, it becomes the primary pitch instrument, and the airspeed indicator is primary for power. Lead the level off by 10% of the rate of climb and adjust the pitch and power to the appropriate settings for the desired level airspeed. Now let's look at descents, which can be made at a variety of rates, airspeeds, pitch attitudes, power settings, and in various drag configurations. You and your instructor should predetermine these power settings and log them on a card for review and future reference. It's also a good idea to show the attitude indicator position expressed in bar widths alongside the power settings for the various flight modes. Later, in preparation for making instrument approaches, you'll want again to determine the power setting for rates appropriate for the airplane you are flying. To enter a descent at constant airspeeds up to maximum structural cruise airspeed, simultaneously lower the pitch attitude and reduce power to the predetermined setting. When entering a descent at an airspeed less than cruise, reduce power to the predetermined setting and slow the airplane in level flight. As the airspeed approaches the descent speed, lower the nose to the predetermined attitude. Make corrections for airspeed by changing pitch attitude, and at the risk of sounding like a broken record, use the attitude indicator to make small pitch changes. Correcting a rate of descent at a specific airspeed requires changing both pitch and power. If you start with a predetermined power setting and pitch attitude, any corrections needed will be small. In order to level off from a descent, you must start your level off before reaching your desired altitude. To do this, lead the level off by about 10% of the rate of descent. As an example, if you are descending at a rate of 500 feet per minute, lead the level off by about 50 feet. To level off at an airspeed higher than descent speed, lead the level off by 20 to 30% of the rate of descent. In the 500 foot per minute example, you would add power and start your level off between 100 and 150 feet before reaching your desired altitude. Turns made while flying by reference to instruments range from shallow compass turns to 45-degree bank steep turns. The usual instrument turn for propeller airplanes is the standard rate turn, which changes the airplane heading at a rate of 3 degrees per second. Variations are usually referred to as fractions or multiples of standard rate, such as half or double standard rate. Faster airplanes turn at half standard rate. However, to maintain a standard rate turn as airspeed increases, your bank angle will also need to increase. At a true airspeed of 100 knots, the bank angle is 15.38 degrees, and at 300 knots true airspeed, the angle required is 39.5 degrees. When flying full panel, the attitude indicator is used to establish the approximate bank angle. You can estimate within several degrees of the angle by dividing the true airspeed in knots by 10 and then adding 7 to the result. At 100 knots, the actual bank needed is 15.38 degrees, and at 300 knots, the angle is 39.5 degrees, while the estimate yields 17 and 37 degrees, respectively. After establishing the approximate bank using the attitude indicator, the turn indicator is used to fine-tune the standard rate turn. If you fly with a turn coordinator, it's simply a matter of lining the wing of the miniature airplane with the left or right index. The most common turn needle has indices on each side of the center index, which are usually called doghouses. If the turn needle is properly adjusted, you are making a standard rate turn when the needle is aligned with the doghouse. A standard rate turn is shown on many glass-equipped airplanes when the heading indicator trend line is matched to a specific index line. In most instrument flying, the bank angle used is the lesser of that for a standard rate, or 30 degrees. If you are fortunate enough to have a flight director, the maximum bank it will command is usually 25 degrees. As you roll into a level turn, use the attitude indicator to set up the estimated angle of bank. For a smooth rollout, lead the target heading by the same amount of turn it took to roll into the turn. Use the attitude indicator to level the wings and the heading indicator to be sure the turn is stopped. As the bank decreases, Relax whatever back pressure was used in the turn and scan the attitude indicator, altimeter, and vertical speed indicator. The magnetic compass, which is usually the only heading instrument left, can only be relied on when the airplane is in straight, level, unaccelerated flight. From your private pilot certificate training, you'll recall that lag and lead and acceleration errors are caused by magnetic dip. During a level turn, the compass can only be believed on headings of east and west. And when accelerating or decelerating, the compass is only truthful on north and south headings. During turns, anytime the airplane is on a northerly heading, the compass will lag or be behind the airplane. On southerly headings, it will lead or run ahead of the airplane. On any headings other than north or south, acceleration will cause the compass to indicate north of the real heading, and during deceleration, indicate south of the real heading. Furthermore, the pedestal mounting of the compass card allows the case to tilt only 18 or so degrees before the card is locked up against the case. Lead, which is greatest on south headings, and lag, which is maximum on north headings, vary with the latitude where the turn is made. An average for the lower 48 states is about 30 degrees maximum, which decreases uniformly as the airplane approaches east and west headings. In a left turn, the airplane is pointing north when the compass indicates 030 degrees. In a right turn, it's pointing north when the compass indicates 330 degrees. Turning to north in a 15-degree bank left turn, the rollout should start when the compass indicates 037 or 038 degrees. In a right turn to south, the rollout should start when the compass indicates 202 or 203 degrees. The problem of lag and lead is further complicated by the question of adding or subtracting the degrees of turn to roll out. Lag and lead can be minimized by making very shallow banks. If you limit banks to half standard rate or less, the compass seems to be more truthful. After attempting to use the compass to turn to headings, pilots become much more enthusiastic about perfecting timed turn technique. For most of us, timed turns work out much better than compass turns. Another trick to use, if a level turn is through east or west, is to time the turn from those headings. The compass is believable on those headings, giving you a reliable intermediate point from which to measure time. Beyond your practical exam, you may have other tools in the cockpit available for heading control after the loss of your heading indicator. In the event of an actual failure, the track indication on your GPS can provide an emergency backup. Even the indications of a handheld GPS may be useful in an emergency. Depending on the equipment, there may be a slight delay in the indication, but it will be consistent for the unit. The GPS track indication can be easier to interpret and to use than the magnetic compass. If you decide to use this indication during an emergency, inform ATC. This will allow the controller to take out the wind correction normally added to heading assignments.
An unusual attitude is any attitude not normally required for instrument flight. This can result from turbulence, disorientation, confusion, or failure of an instrument or instruments. When instruments indicate an unusual attitude, it's important to decide whether there has been an instrument failure, and if there is, whether or not the airplane really is in an unusual attitude. Direction of instrument indication, abnormal indications, or excessive rate of movement call for increasing the cross-check to verify whether it's really an unusual attitude or an instrument malfunction. Based on the indication of this airspeed indicator only, the pilot should reduce power, level the wings, and raise the nose. Now, after checking the other instruments, it's apparent that the airplane is in a nose-high turn to the right. The altimeter and vertical speed indicator both show a climb. With the airspeed approaching the never exceed airspeed, the altimeter and vertical speed indicators should indicate a steep descent. The attitude indicator shows a nose-high banked attitude to the right. The right bank is confirmed by the heading indicator, which is showing heading changing to the right, and the turn coordinator, which shows either a turn or a roll to the right. After checking the other instruments, what at first glance appeared to be a nose-low unusual attitude is a nose-high climbing turn to the right. Both the pitot ram air input and drain hole are blocked, which is causing the airspeed indicator to act as an altimeter. Up until now, you have been taught to have faith in your instruments. This is still true, but if the instruments do not agree, one or more of them must be wrong.
The vacuum gauge, or its equivalent, is an important part of your instrument scan. A low vacuum warning light is better because the light will get your attention even if you have not scanned it. Because of accidents, some airplanes are required to have dual pumps, and there are also standby systems available for other airplanes. Twin-engine airplanes have a pump capable of operating the entire system mounted on each engine. The standby systems include dual vacuum pumps that operate continuously. Electric pumps activate when needed, do the same thing as the engine pump. There's also a system which uses the reduced pressure in the engine intake manifold to suck air out of the gyro cases. Another alternative is electrically operated attitude and heading indicators. Both airplane and independently powered electric instruments are available. The gyroscopes of the heading and attitude indicators spin at up to 25,000 revolutions per minute. Dirty air filters can restrict airflow, which slows the rotor, reducing gyroscopic inertia and making the instruments less stable. Now that you've seen how the vacuum and pressure systems function up close, remember to pay attention to the vacuum gauge during your flights and during the run-up to make sure the system is operating properly. Except for the altimeter and static pressure system check, pilots are not responsible for any rules concerning the accuracy of the flight instruments. However, there are some good operating practices we should follow. When the altimeter is set to the current altimeter setting, note the variation between airport elevation and the indicated altitude. If the variation is plus or minus 75 feet or more, the altimeter should be checked.
If the static source becomes blocked and the airplane climbs or descends, the altimeter will continue to indicate the altitude where the blockage happened, and the vertical speed indicator will stay at the 0 point.
The airspeed indicator measures the difference between static and pitot, or ram pressure. At the altitude where the static was blocked, the airspeed indicator will be correct. At a higher altitude, the airspeed indicator will indicate an airspeed lower than correct. This is because the static side has the lower altitude static pressure, and the ram side has the weaker pressure of the higher altitude. Below the altitude where the static system was blocked, relatively lower air on the pitot side overpowers the weaker air on the static side, resulting in higher than correct airspeed indications. The cure for the blocked static is to use the alternate static source, either an installed system or an emergency system, which is activated by breaking the glass on the vertical speed indicator. In an unpressurized airplane, the alternate static source is vented to the cabin. Using the alternate static solves most, but not all, the problems. Alternate static vented to the cabin will usually cause the airspeed and altimeter indications to be higher than actual. The vertical speed indicator will show a momentary uptrend and then return to its original position. Instrument indications read higher than actual because of the slightly lower atmospheric pressure in the cabin. Back to basic aerodynamics and Bernoulli for a moment. When a fluid flows over a curved surface, there is a velocity increase and a corresponding pressure decrease. The fuselage is a large curved surface, and in flight there is a pressure decrease at the outer skin. Pressure from inside the cabin tends to equalize with the outer skin pressure. The amount of altimeter and airspeed indicator error varies with make and model of airplane, as well as heater and fresh air vent configuration. Newer airplanes have an airspeed and altimeter correction table in the pilot's operating handbook. Pitot blockage only affects the airspeed indicator. When the pitot system freezes or becomes blocked, one of two situations will occur. If only the ram air opening becomes blocked, the indicated airspeed will drop to near zero. If the ram air and pitot drain openings are blocked, pitot or ram pressure is trapped in the system and the airspeed indicator acts like an altimeter. When climbing, the airspeed indicator will increase. The trapped ram pressure is acting against static pressure, which decreases with altitude. When descending, static pressure increases and the airspeed indication will be decreasing. In level flight, large power changes will not change airspeed indications even though actual airspeed changes. Before takeoff, check the vertical speed indicator. It should read 0. If not, gentle taps may return it to the 0 position. Most vertical speed indicators can be adjusted by turning the screw in the lower left corner of the instrument case. If it is not adjustable, use the ground indication as the level flight position. The gyroscopic instruments are powered by either electricity or pneumatic pressure. The electric turn indicator should be checked by turning it on before engine start and listening for unusual noises as the gyro starts spinning. After engine start, engine noise masks any unusual sound coming from the turn indicator. The air-driven gyros for the attitude and heading indicators may take up to 5 minutes to reach operating speed. Set the heading indicator to the compass heading before taxiing. Even though the gyro is not up to full speed, the heading indicator should stay reasonably close to the compass. In flight, precession of not more than 3 degrees in 15 minutes is considered normal. While taxiing, the turn indicator should indicate the direction of turn, and the ball should move freely opposite the turn. The attitude indicator horizon bar should erect and remain stable in the level position within 5 minutes of engine start. If the horizon bar is not level during straight taxiing or tilts more than 5 degrees while making taxi turns, the attitude indicator is not reliable. VORs used for airways have approximately the same power output, but they are classed as low and high VORs. The usable range depends on aircraft altitude, class of VOR, terrain conditions, and other factors. The FAA provides a standard service volume range for each class of VOR. The standard service volume is a planning range for flights between VORs when not flying on a published airway. Published routes may have segments beyond the standard service volume for a VOR, but these will have been flight checked and approved by the FAA. In flight, you may be able to receive and identify other stations with a strong and steady signal beyond their standard service volume distance. If you're at least 1,000 feet above a VOR station and there is no intervening terrain, you should receive en route VORs at least 40 miles away. VORs classed as low have a standard service volume of 40 nautical miles and are used only for the low altitude or Victor airways. HVORs are used for both the Victor Airways and jet routes and have a service volume of as much as 130 nautical miles at altitudes between 18,000 feet and 45,000 feet MSL. However, up to 14,500 feet MSL, the standard range for an HVOR is also 40 nautical miles. Between 14,500 and 17,999 feet MSL, the service volume for high VORs extends to 100 miles. Above 45,000 feet and up to 60,000 feet, this value is also 100 miles.
One of the reasons for the high-low classification is that there are only 80 frequencies available for the approximately 1,000 VORs in the lower 48 United States. It would thus be impossible to protect all of them from frequency interference at higher altitudes.
Let's look at ADF tracking. Let's say you want to track to the station on a bearing of 360 degrees. When that bearing is intercepted, turn to 360. The needle should be right on the nose of the airplane. If there is no wind or it is directly from 360 or 180, the airplane would go to the station on the desired track. There is almost always some crosswind, though, so we have to correct for drift if the airplane is to track to or from the station on a predetermined bearing. If after flying 360 for a few minutes the needle is off to the left 10 degrees, that means that the wind is from the left and the airplane has drifted off course to the right. The first task is to re-intercept. There are rules of thumb on the intercept angle that would be proper. Let's use 30 degrees. When we turn 30 degrees to the left to 330, the ADF needle goes where? If you thought 20 degrees off to the right, you thought correctly. Fly until it is 30 degrees off to the right and you'll be back on track. Leave in 10 degrees to the left for correction and fly 350. The ADF needle will be 10 degrees off to the right, and if this is the correct drift correction, it will remain there. If it doesn't remain 10 degrees to the right with the heading 10 to the left, then some refinement of the drift correction is needed. Intercept again and use either more or less drift correction as the case may be. Let's track outbound on 180. To begin, the needle stays right on the tail. Then the airplane drifts off to the left. The ADF needle will be 10 to the right of the tail position. When we make the right turn of 30 degrees, it will move farther off the tail to 40 degrees. That isn't how it worked when going toward the station, but the next step is the same. When the needle moves back to where it is 30 off the tail, the airplane is back on track. Fly a heading of 190 to allow 10 degrees of drift and see if the ADF needle remains 10 to the right of the tail position. Tracking outbound, both the ADF needle and the heading are to the right if the wind is from that direction. Inbound, the heading was to the left and the needle was to the right. Inbound, opposite sides. Outbound, the same side. Either way, to the station or from, the track that you make good will only be as accurate as your magnetic compass and the setting of the directional gyro with that compass. If your compass were 10 or 15 degrees off and you were flying toward a station, you'd get there, just not on the precise track. Tracking outbound, any compass error will result in you getting farther off the desired track the longer you fly.
Global Positioning System, GPS, and the Wide Area Augmentation System, WAAS, are part of the Global Navigation Satellite System, also known as GNSS.
Aircraft radios used to interact with the GNSS are often referred to as navigators. Older GPS-only IFR navigators are approved as a supplemental navigation system. This means that an alternative means of navigation for the route must be installed and operational. Newer WAAS GPS navigators may be the sole IFR navigation source, but a backup is still a good idea. Both types of navigators allow random area navigation, or RNAV, permitting long, direct IFR flights. Basic GPS uses a network of satellites to triangulate a position anywhere on Earth. There are at least 5 satellites in view at all times. By knowing the precise location of each satellite and matching timing with the atomic clock on the satellite, the navigator can accurately measure the time each signal takes to arrive. The navigator can provide 3-dimensional position and altitude information if it is receiving signals from at least 4 satellites. The signals are line of sight and virtually unaffected by weather. WAAS uses 2 additional geostationary satellites to improve the accuracy of the GPS in the National Airspace System. These satellites transmit a correction signal to WAAS-enabled navigators. The correction signals are calculated on the ground by 2 wide-area master stations and uploaded to the GEOs. These master stations receive signal error data from a network of precisely surveyed reference stations. The reference stations constantly monitor the GPS satellite signals for errors. WAAS augmentation allows more precise position locations both in the horizontal and vertical planes. A GNSS navigator that is approved for en route and terminal operations gives the airplane a slant G suffix when you file the flight plan. Each installation must be FAA approved. The rules require you to have another form of navigation available to fly the approach at the filed alternate airport if the unit is a non-WAAS GPS. For en route and terminal use, you do not have to have a current database, but you do have to ascertain that the waypoints you use in the flight plan are current. A current database is required to fly GPS approaches. An IFR flight plan and an ATC clearance are required to enter controlled airspace when weather conditions are less than required for VFR. The exception is Class A airspace, 18,000 feet MSL, to flight level 600, where an IFR flight plan and clearance are always required, even in VFR weather. Class A airspace lies over the conterminous United States and Alaska, east of 160 degrees of longitude. Airspace less than 1,500 feet AGL in Alaska is also not included. A flight plan and clearance are not required to fly under instrument flight rules or instrument weather conditions in Class G airspace. Recall that ATC has neither the authority nor the responsibility to control traffic in Class G airspace. We can't always have the altitude that we want, especially in busy areas. The minimum en route altitudes, MEAs, shown on charts are often low, especially in flat country. The minimum obstruction clearance altitudes, MOCAs, are even lower when they are provided. The reason a MOCA is lower is that it guarantees VOR navigation coverage only when you are within 22 miles of the station. Seldom could you get a clearance to fly a flight at a MOCA. In many cases, it is even difficult to get a clearance at the MEA. Why? The one thing that is not provided for or covered by these minimum altitudes is radar coverage. Controllers don't like to have airplanes where they can't see them, so they might be more than a little reluctant to clear you at a minimum altitude if they don't have radar coverage. What about flying long direct legs when en route, using approved GPS or other RNAV? This works fairly well, and the controllers have no problem with it in most cases. Do be aware that unless you are flying on airways, no minimum altitude is published for the route. The IFR low altitude en route chart does show an off-route obstruction clearance altitude, or OROCA, within each quadrangle of latitude and longitude. This altitude provides 1,000 feet of obstacle clearance in non-mountainous terrain and 2,000 feet of clearance in mountainous terrain, the minimum clearance required for filing IFR. It does not guarantee radio or radar coverage. Depending on airspace constraints, ATC may direct you to join a published route for some portion of the flight. You will certainly want to have a chart or some other representation of the published route handy for this eventuality. ATC does require radar coverage and monitoring for direct flights. This may mean a higher cruising altitude during portions of your flight. While most airports are in ATC's system, you may need to know the coordinates for an airport if it is not. For example, if you want to request direct to Country Squire Airport, you might have to be ready with North 4521 and West 12216, because the controller in a distance center would have to put those in his computer for it to know where you're going. Another guideline is to plan the direct portion of the flight to begin and end over approximate arrival and departure transition fixes or appropriate nav aids if you're headed to a major area. For example, if you're going to Dallas Love Field from the northeast, they will probably clear you direct to the Bonham Vortac, which is the transition fix from that direction. There's no way they will clear you direct to Love Field. You should plan the route of flight so as to avoid active prohibited and restricted airspace by 3 nautical miles unless permission has been obtained to operate in that airspace. One communication that gives some pilots a problem is the IFR clearance. For best results, it should be written down in rote fashion to be understood later. Don't think about it while writing. Just put down the words the controller says. Next, read them back to make sure you got it right. Then try to understand the clearance. If you file direct to Los Angeles, but the controller comes back with a standard instrument departure that leads into a convoluted routing, the only way you can get it is by writing and not trying to visualize or make sense of the routing as you write. A mind burdened by a question tends to stop even while the controller keeps reading. There's no way to play catch-up when copying clearances. Clearances are read back to the controller unless he specifies otherwise. To reduce frequency congestion, the controller will use the words cleared as filed if the route is the same as that filed on the flight plan. The AIM calls this the abbreviated clearance. The AIM emphasizes that the words cleared as filed apply only to the route filed on the flight plan. Along with the words cleared as filed, the controller will always say the name of the destination airport, the altitude to maintain, and, if a SID is assigned, the name of the SID and transition, if appropriate. The controller will not state the altitude specified on a SID. Another variation is the clearance at an airport without an operating control tower. If there is surface radio communication with ATC, the clearance would be given over the radio. Without surface communication with ATC, the clearance would be received over the telephone. This differs from a normal clearance in that a release time and a void time are usually given as part of the clearance. A release time means that the departure airspace is not available until that time. Very simply, it is the earliest time for takeoff. Void time is the latest time for takeoff. In order to use the departure airspace, the airplane must take off by the void time. Pilots who take off at or after the void time are not afforded IFR separation and may be in violation of the rule which requires a clearance to operate under IFR in controlled airspace. Because airspace is reserved for departure aircraft, pilots who do not depart by the void time must notify ATC as soon as possible, but not more than 30 minutes after void time. If ATC has not been contacted, search and rescue is initiated 30 minutes after void time. Clearances will sometimes specify that ATC must be advised that the airplane did not depart in less than 30 minutes after the void time. Our terminal area procedures with ATC begin on departure. On most of that flying, the clearance by ATC takes care of everything. The clearance may be simple, such as direct to a VORTAC, then on course. It may be complicated, such as some of the standard instrument departures, or SIDs. A SID is a graphic departure procedure designed by ATC to standardize traffic flow, ensure aircraft separation, and provide obstacle clearance from the terminal area to the en route environment. SIDs are published in the Terminal Procedures publication alongside the approach charts for an airport. You cannot fly a SID without a specific ATC clearance to do so. If ATC assigns you a SID that shows the departure control frequency, they might save some time and not mention that frequency when issuing your clearance. If you don't wish to use standard instrument departures, you should note this in the remarks section of your flight plan. If they give you a SID anyway, it is your responsibility to inform the controller. At that point, you should be furnished with appropriate departure instructions. Another type of instrument departure is the ODP, or Obstacle Departure Procedure. Unlike a SID, which is always printed graphically, an ODP may be either textual or graphic. Textual ODPs are printed in Section C of the Terminal Procedures publication, while graphic ODPs are named and printed alongside the approach charts for an airport, just like the SIDs. You can tell them apart because a graphic obstacle departure procedure has the word obstacle in the title. ODPs do not require an ATC clearance, and you should plan on flying the ODP if the weather is anything worse than day VFR, unless ATC has assigned you a SID or radar vector that's different from the ODP. If an ATC clearance conflicts with a published ODP, be sure to clarify this with ATC. A controller is not permitted to lower or cancel a minimum altitude specified on a SID or an ODP. Regardless, you are ultimately responsible for the safety of your flight. An inverse T printed in the notes section of FAA approach charts indicates that the airport has a published departure procedure and/or non-standard takeoff minimums. If you see this symbol, refer to Section C of the TPP to see if there is a departure procedure for that airport. The takeoff minimums do not apply to Part 91, not for higher operations, but it's a good idea to abide by them anyway, especially in unfamiliar terrain. Any obstacles will still be present regardless of the operating rules for your flight. The takeoff minimums may provide a chance to see them before it's too late. The standard takeoff minimums that apply to for higher operations are 1 statute mile if an airplane has 1 or 2 engines, and 1/2 mile for airplanes with 3 or more engines. Non-standard takeoff minimums will vary. In this example, at Harrison, Ohio, the takeoff minimums for runway 1 are a 500-foot ceiling and 3 miles visibility. The standard takeoff minimums can be applied if the airplane can climb at least 385 feet per nautical mile to 1,200 feet MSL. For Jeppesen users, textual ODPs are printed on the approach chart. If you're departing from an airport that is in Class G airspace, your clearance will start out with something like
Planning controlled airspace, fly heading of 180, climb and maintain 3,000.
That's a polite way of telling you that you are indeed on your own when in Class G airspace.
A clearance variation sometimes used at the arrival end of an IFR flight is the cruise clearance. Cruise clearances are used for relatively short flights in uncongested airspace.
Instead of clearing the aircraft to maintain an altitude, the cruise clearance is initiated when the controller clears the aircraft to cruise an altitude. A cruise clearance allows the pilot to select any altitude between the minimum for IFR and the cruise altitude specified. For instance, cruise 6,000 means the pilot could climb or descend within the block from 6,000 feet and the minimum for IFR. The report without request when vacating a previously assigned altitude is not required. However, if the pilot does report descending from an altitude, the aircraft may not return to that altitude without ATC clearance. A cruise clearance authorizes the pilot to fly to and make an approach at the destination. The controller who issues the cruise clearance knows that there are no other IFR aircraft on that set of airways at or below the cruise altitude. In addition, there are no IFR aircraft inbound to the destination within the time for the cruise aircraft to make an approach.
By saying cruise, the controller means there is no traffic, and we don't have to be so formal about this flight.
After giving an IFR clearance, ATC doesn't consider the clearance transaction complete until the pilot has acknowledged receipt and understanding of the clearance. Pilots are expected to request clarification or an amended clearance if the clearance is not understood or is unacceptable. If a clearance would cause a deviation from a rule or regulation, the pilot is responsible to request an amended clearance. Pilots are expected to comply with any instruction upon receipt. When expeditious compliance is necessary, ATC will include the word immediately to impress urgency. When a turn is requested or a heading is assigned, pilots should promptly make and complete the turn. The new heading should be maintained until other instructions are issued. When departing from a tower-controlled field, don't change to departure control until the tower instructs you to do so. This is true whether or not you have entered the clouds.
Sometimes the term "at pilot's discretion" is included in altitude clearances. This means the pilot has the option to start climb or descent whenever he or she wishes.
Climb or descent may be made at any rate, and if desired, the pilot may temporarily level off at an intermediate altitude. However, once an altitude is vacated, the pilot may not return to that altitude. When the term "at pilot's discretion" is not included and no climb or descent restrictions have been imposed, pilots should begin the climb or descent promptly on acknowledgement of the clearance. Descend or climb at an optimum rate consistent with the operating characteristics of the aircraft to within 1,000 feet of the assigned altitude, and then at a rate between 500 and 1,500 feet per minute. If at any time you cannot climb or descend at least 500 feet per minute, tell ATC. If a controller tells you to resume own navigation, that means that any radar vector that you had been flying is complete, and it is your responsibility to navigate from here on. When airborne, pilots should read back those parts of ATC clearances which contain altitude assignments or vector headings. This serves as a double check between pilots and controllers and reduces communications errors which happen when a number is misheard or is incorrect. All readbacks and acknowledgments should be preceded by the aircraft identification. Altitudes, altitude restrictions, and vector headings should be read back in the same sequence as issued. While SIDS and ODPs cover departures, there are STARs, Standard Terminal Arrival Routes, for arrivals. The name is descriptive. They are nothing more than standard routes into the terminal area that generally end at a fix from which you will be vectored to the final approach course. If you do not wish to fly a STAR, note that fact in the remarks section of your flight plan. Then, theoretically at least, you won't be issued one. If you are given a STAR anyway, tell the controller and you should receive appropriate instructions. Let's take a look at a STAR, the Finger 3 arrival to the Dallas area. Scary looking, isn't it? It's relatively simple, though. Most of the detail on the chart depicts the many transitions to finger. The nub of the matter is on the next page in words. If you're flying from Fort Smith, Arkansas, for example, the actual Finger 3 arrival involves flying over the Bonham Vortac and then following the Bonham 191-degree radial to the Finger intersection. Then turn southwest and fly the Cowboy 046-degree radial 8 miles to the slant intersection. If traffic is landing north, depart slant on a 190-degree heading for vectors to the final approach course. If you'll be landing south, ATC will give you vectors from slant to the final approach course. If you're flying to Love Field from the northeast, just plan a route that comes over any of the transition fixes, then the Finger 3 arrival, coded FINGR3, and ATC will love you. The architecture of the system is such that a descent gradient of 250 to 350 feet per nautical mile is expected of arrivals. If you're steaming into a terminal area at 180 knots ground speed and can't manage a descent rate of from 750 to 1,000 feet per minute, you might anticipate requests to descend more rapidly and perhaps some radar vectors for spacing. At 120 knots, 500 to 700 feet per minute would be the magic number. If it's a busy airport with automatic terminal information service, ATC will expect you to have listened to that before calling. The dealings with ATC after that are straightforward. They assume that you know the approach in use, and the most likely handling at an airport without stars would include the assignment of ever lower altitudes and vectors to intercept the final approach course of the runway in use. Separation from other aircraft in a terminal area may be either vertical or horizontal, but sooner or later the controller has to get all the airplanes lined up and headed for the runway at the same altitude with the proper separation. The controller will normally tell you if it will be necessary to vector across the final approach course for spacing or other reasons. If the final approach course is coming up and you haven't been cleared for the approach, ask the controller if you should turn inbound on final. Don't turn inbound until you have either been cleared for the approach or cleared to intercept and track the final approach course. When you're being vectored, the lowest altitude you will be assigned is the minimum vectoring altitude. This altitude meets IFR obstacle clearance altitudes, but it may be lower than the minimum altitude shown on your chart. It is utilized only after the controller determines that the radar return from the aircraft is adequate. Minimum vectoring altitude charts are normally available only to controllers. Once inbound on the final approach course, cleared for the approach, the controller expects the pilot to either complete the approach or execute a missed approach at the appropriate time.
ATC does like to know when you're on the ground. If you are landing at a controlled airport, the tower will handle this for you and will automatically cancel IFR. At other airports, you can either cancel with ATC on the radio before landing or through a flight service station. Otherwise, the controller will ask you before you land if you're familiar with the cancellation procedures for that airport. This is usually a phone number to call at the TRACON. Holding may be encountered in any phase of an IFR flight. Some departure procedures call for climbing in a holding pattern.
En route, you must hold if you've not been cleared to your destination and have reached your clearance limit. On arrival, many approach procedures use a holding pattern for the course reversal, and all missed approaches end up in a hold. Holding patterns are as charted, or as given by the controller. For a hold that is not charted, the controller will tell you what direction to hold, the holding fix, the bearing or airway upon which to hold, leg length if necessary, the turning direction if it is left, and the expect further clearance time. The end of the inbound leg is marked by the holding fix. This may be a navade, waypoint, intersection, or DME distance. To begin, you fly to the holding fix. You should slow to holding speed at least 3 minutes before reaching this fix. Holding speed will vary by airplane, but it must not be faster than the maximum speeds published in the AIM for your altitude. Some holding patterns have different speed limits charted. The standard holding pattern uses right turns and a 1-minute inbound leg up through 14,000 feet, 1.5 minutes above 14,000 feet. Some holding patterns specify a DME or RNAV leg length instead of time. If you are holding at a VOR, start your outbound turn at the first complete reversal of the to-from indicator. Start timing the outbound leg when either above or abeam the fix, whichever is later. If you can't determine when you're abeam, start timing when the outbound turn is completed. At 14,000 feet and below, use 1 minute for the first outbound leg, and adjust the timing on the subsequent outbound legs to compensate for wind to make the inbound leg 1 minute. Turns should be standard rate, but not more than 30 degrees. If you're using a flight director, the maximum bank angle is 25 degrees. Except when turning, you should compensate for the wind. Outbound, you should triple the wind correction angle used to track the inbound course. This will distort the racetrack shape, but keep you inside the holding pattern protected airspace. The protected airspace is not charted, but it is shaped somewhat like and centered upon the holding pattern. This puts about 60% of the protected area on the holding side, so the majority of your maneuvering should be there. How much airspace is protected? The FAA uses 31 different templates for holding pattern protected airspace to fit over 100 combinations of altitude, fixed to navade distance, and airspeed. The smallest size, used only up to 4,000 feet, is 6.7 nautical miles wide. Up at 46,000 feet, where the wind blows stronger and the jets fly faster, the FAA uses a pattern that is 57 miles wide. The miles of protected airspace are there to allow for dead reckoning on the holding pattern entry and on the outbound legs in a minimum 50-knot wind. This is not an excuse for sloppy flying in a holding pattern. Staying safe depends on compensating for the wind and following the recommended procedures. The FAA holding pattern entries are designed to transition you into the hold with a minimum of turning while keeping you in protected airspace. For the instrument knowledge test, you must know when to use the parallel, teardrop, and direct entries. On the flight test and in real life, you may use any method that keeps you in the protected airspace, and we'll cover some alternate entry methods in a minute. Flying toward the holding fix, look at where the outbound course falls on your heading indicator, or HSI. Divide the indicator into 3 segments, like so, for a standard right turn hold, and you can visualize exactly what kind of entry the FAA expects of you. Note that this visualization on the heading indicator is simply the FAA entry pattern diagram flipped and rotated so that the teardrop section is on the upper right. The teardrop section is the smallest, only 70 degrees on the right of the nose. At the fix, turn to a heading 30 degrees from the outbound course toward the holding side for 1 minute. Then, turn in the direction of the holding pattern to intercept the holding course. The direct entry section is the largest, covering a 180-degree arc. Simply turn right outbound and fly the pattern. The parallel segment is the 110 degrees to the left of the nose. Turn to the outbound heading, correct for wind if known, fly for 1 minute, and then turn toward the holding pattern more than 180 degrees. Return to the holding fix or intercept the holding course inbound. Note that a parallel entry is only truly parallel in a no-wind condition. Many pilots prefer the additional precision afforded by tracking the inbound course outbound instead of the FAA's dead reckoning parallel entry. A non-standard holding pattern uses left turns, and the entry procedure diagram has to be flipped so the teardrop section is in the upper left. A rule of thumb can help you visualize the entry needed. For non-standard left turns, use your left thumb to mark the 70-degree teardrop section, and the remaining sections fall into place. Right turns, right thumb. There are also devices available to help determine the correct entry. These diagrams can be difficult to visualize in the cockpit, so some instructors recommend simply flying a teardrop anytime you can't use a direct entry. An old Air Force method takes the opposite tack and suggests flying a parallel entry whenever the direct entry isn't possible. Both of these alternatives may involve a little extra turning, but they'll keep you in the protected airspace and minimize mental math.
Instrument approaches are divided into precision, non-precision, and approaches with vertical guidance.
A non-precision approach is a clearance to descend at a fix to an MSL altitude called a minimum descent altitude, or MDA. The airplane is then flown in level flight at the MDA with the pilot hunting for the airport. If the airport or runway is not in sight at a certain time or point, the hunting license expires. The missed approach comes next. The missed approach for some non-precision approaches starts on the basis of ground speed and time to fly from the final approach fix to the missed approach point. Other approaches have a fix where the missed approach begins. On precision approaches, the airplane intercepts and follows the glide slope to an MSL altitude called the decision altitude, or DA. If the runway environment is not in sight at the DA, the missed approach comes next. Incidentally, some use the term decision height instead of decision altitude. Decision height is really the height above the threshold elevation. Like a precision approach, an approach with vertical guidance has both course and glide path information, but it is not as accurate as a precision approach. A clearance for an instrument approach is authorization to descend to the MDA or DA as appropriate while following the procedure. In order to descend below the MDA or DA, you must have the runway itself, runway markings, or approach or runway lights in sight. In addition, the flight visibility cannot be less than specified on the approach chart, and the aircraft must be in a position from which a descent to the runway can be made at a normal rate. If these conditions do not prevail at the missed approach point or DA, you must make a missed approach. If a descent from DA or MDA is started, and because of low fog or other restrictions to visibility the required conditions no longer exist, a missed approach must be made.
There are two approaches that are not procedural and are based on a deal between the pilot and the controller. They are the visual approach and the contact approach. The visual is literally visual.
You must have the airport or an identified preceding aircraft to follow in sight before a visual approach will be approved. Because a visual is not a procedure, there is no prescribed missed approach. This is generally no problem because visuals are used only in good weather, but if you need to abort a visual approach at a tower-controlled airport, tell them about it and they will tell you what to do next.
If you have to abort a visual approach at an uncontrolled airport, you are expected to remain in VFR conditions and contact ATC as soon as possible for further instructions. This is something that might happen, for example, when a shower moves over the airport after the clearance for a visual has been given. Visual approaches are initiated by ATC. Pilots have to request a contact approach.
You must be clear of clouds and have a mile flight visibility and a mile visibility reported at the airport for a contact approach. The airport must have an approved instrument approach procedure. The pilot is responsible for obstruction clearance during a contact approach. These can be useful, but chancy if not used with caution. The best use might be where you see the airport as you are maneuvering for an instrument approach, are in a position from which a normal landing can be made and you don't wish to fly the whole instrument approach procedure. If a contact approach were to turn into a missed approach, ATC should be advised. Approach charts are a detailed blueprint for an instrument approach. Nothing is omitted or left to the pilot's imagination. There are specific instructions for each part of the approach. With some minor differences, FAA and Jeppesen approach charts both give a from top to bottom presentation of information about the procedure. To get started, the top of the chart has the pilot briefing information. For the initial approach segment, the necessary information is in the plan, or bird's eye view. The approach has already started when the most pertinent information is in the profile view. The approach is almost finished when the information about how low you can go and the flight visibility required is in the minimum section. When you look at an approach chart, review the pilot briefing information area first. The top row of boxes has the primary navigation information, final approach course, and airport and runway data. The next row contains procedure notes and restrictions, icons if non-standard alternate and/or takeoff minimums apply, approach lighting symbols if installed, and then the missed approach procedure. The third row has the communications frequencies in the order needed during an approach. The most common error when tracking a localizer is making large heading corrections. This results in making S-turns across the center line. When you are on the localizer center line, fly the inbound heading until the CDI moves off center. Before passing the outer marker, heading changes of 5 degrees or less should keep you on the center line. Because the localizer gets narrower as you fly closer to the runway, heading corrections should be proportionally smaller. Inbound from the outer marker, usually 4 to 7 miles from the runway threshold, heading changes should be limited to 2 degrees at a time. This doesn't mean you can't make consecutive 2-degree heading changes.
The new heading will do one of 3 things. It will slow down the rate at which you are leaving the center line. It may keep you the same displacement from the center line, or bring you back to the center line. Be patient. Give the new heading a chance.
Marker beacons provide distance information. The marker beacon antenna is designed to transmit the signal straight up like a searchlight. The signal pattern is an ellipse perpendicular to the localizer center line. At 1,000 feet above the antenna, the signal is about 4,800 feet wide and 2,400 feet thick. The aircraft must be located within the ellipse to receive the signal. To have the most precise fix, marker beacon receivers which have sensitivity selection should be in the low sensitivity position. All marker beacons transmit on 75 megahertz. Backcourse markers are fairly unusual. They are used for a final approach fix on a localizer backcourse approach. Touchdown zone lights are lights embedded in the first 3,000 feet of the runway, while centerline lights illuminate the middle of the runway along its entire length. Runway visual range, RVR, is machine-measured horizontal visibility near the approach end of the runway. The glide slope needle points to the center line of the glide slope. This is a fly-up indication. This is a fly-down indication. Because the glide slope is a reflected signal, it's possible to receive indications anywhere around the antenna. Glide slope indications should be disregarded unless the approach chart specifies a glide slope. Because of the reflected signal, false glide slopes are above the real glide slope. The lowest false slope is more than 10 degrees to the horizontal. Approach procedures are designed to prevent intercepting a false glide slope, and the high descent rate required would warn the pilot. The lowest possible false slope would require a descent of more than 1,000 feet per mile. The rate of descent to stay on the glide path is a function of the ground speed. At 90 knots ground speed, the descent needed is 478 feet per minute. To find the approximate descent rate, divide the ground speed in half and multiply that by 10. At 100 knots, this yields 500 feet per minute as the approximate rate of descent. You should know the power setting for a 3-degree descent at ground speeds appropriate for your airplane in the approach configuration. The rate of descent tables are in the FAA approach chart books and on Jeppesen charts. Before intercepting the glide path, you should estimate your average ground speed based on the wind at your altitude and the surface wind. As the glide path is intercepted, reduce power to the setting that gives the proper descent for the estimated ground speed. Any deviations from the glide path less than half scale should be corrected by making pitch changes only. Remember, at the outer marker, a half scale is only about 200 feet and decreases to 25 feet at the middle marker. If the deviation is more than half scale, or if it is happening quickly, a power change must be made. Power changes should be small. If your estimated setting was anywhere in the ballpark, a change of 50 RPM for fixed pitch propellers or half an inch of manifold pressure for constant speed propeller airplanes should be adequate to return the airplane to the glide path without a substantial speed change. On the profile view of the approach chart, the glide slope intercept altitude, which is also the final approach fix, is shown by the lightning bolt. Glide slope angle and projected threshold crossing height are also depicted on the profile view.
Procedure turns are used to reverse direction and establish the aircraft inbound on an intermediate or final approach course. The altitude shown on the chart for a procedure turn is a minimum, and the maneuver must be completed within the distance shown on the chart. The distance is usually 10 miles, but may be 5 where only Category A airplanes and helicopters operate, or may be extended to 15 miles to accommodate high-performance aircraft. Both this distance and the side of the course on which the procedure turn are charted are critical because only by following the procedure are you assured of terrain and obstruction clearance. A procedure turn is a required maneuver except when the symbol No PT is shown, when the aircraft is being radar vectored for the approach, when conducting a timed approach, or when the procedure turn is not authorized. On the ILS to runway 10 at Millville Municipal Airport in New Jersey, for example, no procedure turn is required if you fly the transition shown from the Smyrna Vortac. The most common procedure turn is the 45-degree type. Fly outbound, do a 45, a 180, and then intercept. Some pilots use an 80-degree, 260-degree course reversal instead of the 45. This is fine. Just be sure it is done on the correct side of the outbound course. If the chart shows a procedural track, such as a teardrop, where you fly outbound on one radial and then turn and fly inbound on another, that procedure must be flown as charted if you do a procedure turn. Another example of a procedural track would be a DME arc. At Beeville Municipal in Texas, the DME arc is at 2,000 feet, 9 miles from the Three Rivers Vortac. Many of the procedure turns charted now appear as holding patterns at an intermediate fix or the final approach fix. The holding pattern maneuver is considered complete when the airplane is established inbound after the appropriate entry. If cleared for the approach while in a holding pattern, and if the aircraft is at the prescribed altitude, no additional circuits in the hold are required or expected. If it were to be necessary to fly another pattern to lose altitude, the controller should be informed.
Talk to enough instrument pilots, and you'll find at least one who will insist that an NDB approach is an emergency procedure. It's too bad that this procedure has gotten a bad name in some circles, because NDB approaches have a lot going for them.
A non-directional radio beacon is relatively inexpensive. The site requirements are minimal, and before GPS, an NDB was often the only practical way to make the airport a part of the IFR system. There are two basic kinds of NDB approaches. The most common one is with the NDB located on the airport. This is also the simplest one to fly, as well as the one that will lead you most precisely to the airport. With the aircraft on final approach, the ADF needle simply points at the airport. What more could you ask? The other type NDB approach would be with the beacon away from the airport. In all of this, we have ignored the possibility that the airplane might have an approach-approved GPS. If it does, there may be an overlay GPS approach, and then you can use the GPS to fly the NDB approach with a lot more precision.
Even if your GPS is not approach-approved, or if you have a VOR DME area navigation unit, it's foolish not to back up the ADF with the additional information available from another source.
The approach chart designates a straight-in landing runway if there is one. Landing on another runway requires circling, and different minimums apply. For a straight-in approach, the angle between the intersection of the extended center line of the runway and the final approach course cannot exceed 30 degrees, or 15 degrees for GPS approaches. A circling-only approach is either not aligned with a runway, or in the case of a few procedures, one where a straight-in would require an excessive descent on the final approach segment. On a circling approach, the charted approach procedure is flown until the airport or runway is in sight. One of the ground rules for a circling approach is that the pilot must maintain visual contact with the airport during the circling maneuver. Regulations state that a missed approach must be made if an identifiable part of the airport is not distinctly visible while circling at or above the MDA. The one exception is if a normal bank causes the inability to see the airport. Recall the ground rule for all approaches, that descent from MDA or DA cannot be made until the aircraft is in a position from which a descent to a landing can be made at a normal rate of descent using normal maneuvers. Aircraft approach categories are primarily established for circling approaches. The size of the circle flown is related to the speed of the aircraft squared. Twice the speed quadruples the radius of the turn. The obstacle clearance area for circling approaches is determined by connecting arcs which extend from the center of the runway ends. MDAs for A category circling approaches are determined by arcs which extend 1 3/10 of a mile from the end of the runways. This distance is increased for each successive category. If you circle an aircraft at a speed higher than its category, you must use the minimums for the higher speed. For example, a Category A Skyhawk being maneuvered at 100 knots would have to use Category B approach minimums. Circling MDAs may be less than 400 feet and as high as 1,000 or more feet above the airport elevation. Circling an airport at an altitude of less than 400 feet AGL in a slow airplane in marginal weather conditions while concentrating on keeping the airport in sight can present a lot of problems. On a circling approach, you are expected to maneuver by the shortest path to the base or downwind leg. There is no restriction against flying over the airport or other runways. If the ceiling permits, fly over the airport to observe the wind direction indicators and look for other traffic. Some procedures have limitations on where you can circle due to terrain or obstructions. These will be noted in the procedure notes section on the top left of the chart. If a landing cannot be made, a missed approach must start at the missed approach point. The published missed approach or an alternate procedure specified in a clearance must be followed. If visual reference is lost while circling, the missed approach should start with a climbing turn toward the landing runway. The turn should be continued until established on the missed approach course. Now let's take a look at GPS approaches. Because GNSS navigators contain so much information and capability, you do have to learn to use each unit. You should read the GPS manual and utilize available training software. The unit may also have a simulation mode to use for ground practice. The manuals and training aids are great for learning the switchology, but you do have to fly some flights and approaches with a GPS to really learn to use the navigator. It's generally required that both the flight manual and supplement and the pilot's guide for the GPS navigator are available to the pilot whenever the equipment is being used under IFR. Always fly with a safety pilot when learning GPS because it requires a lot of head-in cockpit time. This should be done in VFR conditions. GPS approaches will include the letters GPS in the title of the procedure. The approach may coincide with a non-precision approach utilizing ground-based nav aids. These overlay approaches will display approach minimums in the familiar straight-in or circling format. An overlay approach can be identified by an OR in its title. The NDB or GPS Runway 8 approach at Lakefield in Salina, Ohio is an example. Standalone GPS approaches will be titled as simply GPS or as RNAV GPS. These approaches were designed specifically for GPS navigator use. Older standalone approaches may use the traditional straight-in or circling format. Newer approaches describe the minimums using one or more of the labels LPVDA, LNAV/VNAVDA, LNAV-MDA, and circling. Standalone GPS approaches are typically designed to minimize course reversals. When a course reversal is associated with an initial approach fix, it's often performed using a holding pattern. In order to fly any approach using the GPS as your primary navigation source, the database must be current. The approach must also be defined in the database and loaded from there. The navigator will not allow an approach if a feature called RAIM, Receiver Autonomous Integrity Monitoring, does not assure that the available satellite geometry will allow the receiver to calculate a position within a specified protection limit. RAIM needs a minimum of 5 satellites in view, or 4 and a barometric altimeter input from an altitude encoder. WAAS navigators can utilize a WAAS geostationary satellite as an additional pseudo-GPS satellite. Let's plan to fly the RNAV GPS approach to runway 19 at the Cincinnati West Airport in Harrison, Ohio. We'll demonstrate the approach with the Garmin 430W. As before, you must thoroughly know the unit installed in your airplane for operations under IFR.
Much of this approach chart is similar to what you've seen on other procedures. There are a few items that are unique to GPS standalone approaches. We'll take a look at those items before flying.
Notice on the plan view that you have your choice of 3 initial approach fixes on this procedure. Your route toward the approach should define the most logical choice for an initial fix. The approach looks like a T with a holding pattern course reversal at the center initial approach fix, also labeled as an intermediate fix. When Kirk's is used as the initial fix, the holding pattern must be used for the course reversal if one is required. If you are approaching from the north and ATC has cleared you for the approach with Kirk's as the initial fix, the controller won't expect you to enter the hold. If you need a turn or two in the hold to lose altitude, just ask. Note that the holding pattern is defined by mileage from the Kirk's waypoint. This is common with GPS-based holding patterns. Pilots using HOMOR or JBIRT as the initial fix should not fly a procedure turn. Simply make the 90-degree turn to fly by Kirk's and join the final approach course. Notice the difference between the symbol for the missed approach point waypoint and the others. The missed approach point is a flyover waypoint, meaning you must do exactly that, fly over the waypoint. The other waypoints are shown as fly-by waypoints. With a fly-by waypoint, it is perfectly acceptable to fly over the waypoint, but it is also okay to fly by the waypoint when turning. The turn anticipation feature of the 430W will do this automatically to prevent you from overshooting the next course. This procedure uses a standard MSA circle. Many procedures for T-shaped GPS approaches use terminal arrival area quadrants to define minimum safe altitudes. The TAA sections may also add instructions such as no PT for arrivals from that area. This procedure is not authorized from the transition fixes when you arrive from particular directions along the noted airways. These restrictions make sense when analyzed and can be avoided with some planning. The minimum section has an LNAV-MDA for straight-in landings and circling minimums. In the case of this approach, they are the same, though that is not the norm. With only the LNAV line for the straight-in approach, any vertical guidance provided by the 430W is advisory in nature only. It's still considered a non-precision approach and subject to the same MDA rules as other non-precision approaches. The vertical guidance simply allows the approach path to be more stabilized and reduces workload. A good rule of thumb is, if you have advisory vertical guidance available, use it. A non-WAAS 430 will not provide any vertical guidance on a GPS approach. At 3,000 feet, we're approaching the area from the southeast with Cincinnati West, India 67 flight planned as our destination. We're within 30 nautical miles of our destination, and the 430W has set itself to terminal mode. Terminal mode changes the scale of the CDI full deflection to 1 nautical mile either side of the course. During the en route phase of the flight, the scale was set to 2 miles. ATC has advised us to expect the GPS 19 approach. To load this into our flight plan, press the Procedures button. Ensure Select Approach is highlighted and press Enter to bring up a list of available approaches. Highlight the GPS 19 using the large right knob and press Enter to open the Transitions list for the approach. Considering our direction of flight, Homore is our likely initial fix. Select this and press Enter. At this point, the 430W wants to know if we would like to load or activate the approach. Loading it adds the approach to our flight plan, but doesn't change our current course. We'll do that for now. The waypoints and legs for the approach appear on the map, but their lines are thin to show they are not an active part of the flight plan. ATC has now cleared us for the approach, so we need to activate it. Press the Procedures button, select Activate Approach, and press Enter. The 430W plots a course from our present position to Homore. The other legs of the approach are now more prevalent on the map display. Check the message to determine the course to set in the OBS. While the OBS setting does not affect the action of the CDI when flying in leg mode, it's a good practice to set this course in the top of the OBS. Doing this will also clear the message indication. Approaching Homore, the 430W advises us to plan a left turn to 276 degrees and begins a countdown. This is followed by turn left to 276 degrees now. Note the turn anticipation line on the map that takes us beside Homore. As we are turning, the approach leg from Homore to Kirks becomes active. The message indicator begins flashing and tells us to set the OBS to 275. Approaching Kirks, additional turn messages appear. Aligned with the final approach course and approaching the final approach fix, the status changes from terminal to LNAV plus V. This indicates that the 430W has verified RAIM and the approach is active. This permits us to descend at the final approach fix. The plus V indicates that the 430W will be providing us with the advisory vertical guidance discussed earlier. Beyond the vertical guidance, our approach chart tells us that we can descend to 2,500 for the next leg to Davie, the final approach fix. 2 nautical miles prior to the final approach fix, the 430W starts reducing the scale of the CDI deflection again. This WAS-approved box will continue to decrease the scale until near the missed approach point. This simulates the angular deflection that you would normally find on an ILS or VOR approach. Non-WAS boxes use the 2 nautical mile point to verify RAIM and go active. They also scale the CDI deflection, but only to 0.3 nautical miles full scale deflection. This value is reached at the final approach fix and remains constant to the missed approach point. Passing Davie, we have the option of flying the approach just as we would any other non-precision approach. That is, we could begin a descent that would allow us to reach the MDA well before the missed approach point. We would continue at the MDA until able to land or required to miss the approach. Using our vertical guidance rule of thumb, we will make a stabilized approach by following the advisory guidance to the MDA. This allows the approach to be flown like an ILS. The difference is that we cannot descend below the MDA even while transitioning to the missed approach unless conditions are right for landing. Crossing the missed approach point, the Suspend label appears above the OBS button. Pressing this button activates the missed approach procedure. We'll start our climbing right turn to 3,000 feet and return to Kirks for the hold. Approaching Kirks, the 430W advises us the most appropriate holding entry for our route of flight. Now let's look at the RNAV GPS approach to runway 29 at the Butler County Airport in Hamilton, Ohio. This is another standalone GPS approach, but it includes LPV and LNAV VNAV minima lines. These approaches are classed as APV approaches. APV approaches have vertical guidance and a decision altitude, but do not meet ICAO standards for a precision approach. Most IFR-approved WAS navigators can fly an LPV or LNAV VNAV approach. Check your flight manual supplement to be sure. Non-WAS GPS navigators will still need to use the LNAV or circling criteria. Our Garmin 430W is approved for the LPV approach, and that is what we will plan to fly. Looking at the notes at the top of the chart, you may notice something called Baro VNAV mentioned. This is a non-WAS technology that, if approved, could allow some older navigators to fly using the LNAV VNAV minima. It's unlikely that you'll find this system in a smaller airplane. Baro VNAV, when installed, is typically only found in an airplane with an FMS computer. The profile view shows a step-down altitude at Punu. The asterisk beside the altitude points to a note indicating that it applies to LNAV only. Flying the LPV approach, we don't need to be concerned with the altitude unless the navigator downgrades the approach. This could occur during the RAIM check due to a WAS outage or anomaly. Our decision altitude for the LPV approach is 944 feet. This puts us 325 feet above the touchdown zone elevation. The LNAV MDA is nearly 200 feet higher. Approaching Hamilton from the east, we load the GPS 29 approach into the 430W and activate vectors to final. Since we are getting vectors and there is no need for a course reversal, we will disregard the holding pattern at Burney. Passing Burney, we can descend to 2,600. The approach is active as shown by the LPV on the screen, and the glide slope needle has come alive. We'll intercept and track the glide slope at Holger. Like an ILS, we set a descent rate and power setting to keep the glide slope needle centered. Reaching our 944-foot decision altitude, we must decide if we can continue and land or if a missed approach is in order. In our case, the runway environment is in sight and we can proceed with our landing. The final approach that we will look at with the 430W is the VOR or GPS Alpha approach at Gene Snyder Airport in Falmouth, Kentucky. This is an overlay approach with only circling minima. The 430W makes the approach easy to fly. We are approaching the Falmouth VOR from the north at an ATC assigned altitude of 3,000 feet. We are cleared for the full approach. We'll load the approach in the navigator and activate it with FLM as the initial approach fix. Approaching the VOR, the 430W commands a turn to intercept the outbound course for the approach. Approximately 1 nautical mile from the VOR, the 430W has plotted a procedure turn. While you can use any style of procedure turn on this approach that keeps you south of the course, we will follow the plotted course. Turning inbound on the approach, the 430W goes active for an LNAV approach. This approach will not provide any advisory vertical guidance. We can descend to 2,500 feet. Crossing the final approach fix, the location of the VOR, we can begin our descent to the MDA of 1,500 feet. If we were flying the approach with only a VOR, we would need to start a timer at the final approach fix. With the 430W, we are tracking toward a computer navigation fix called Majib. Majib is the missed approach point, allowing us to continue without keeping track of the time. Crossing Majib, Suspend appears over the OBS button. Pressing this button loads the missed approach procedure just as on any other GPS approach. A GPS-based approach on the integrated Garmin G1000W is very similar to the 430W. The CDI on the HSI and any glide slope indication by the altimeter will be magenta when flying a GPS-based approach. The phase of flight and the GPS mode will be indicated in the center of the HSI where it's easy to find. The CDI's OBS pointer on the HSI will also auto-slew as the course direction changes.
That wraps up our review of GPS procedures and approaches. As you saw, a modern GPS navigator can make these operations very simple if you know how to use the unit. Take some time to learn your box well. It'll make its use under IFR much more relaxed and effective. Partial panel, or what is sometimes called emergency instruments, is controlling the airplane without the attitude and heading indicators. In most light airplanes, the gyroscopes for the attitude and heading indicators are powered by a vacuum or pressure pump, which is mounted on the engine accessory case. The gyroscope for an analog turn indicator is usually electrically powered, giving you wing level ability in case of a pump failure. The attitude indicator is usually the first instrument to slowly show a pump failure, usually by incorrect pitch indications. An additional problem is that it usually ends up showing a nose-low banked attitude.
To get some notion of how vacuum-driven instruments react to a power failure, sit in the airplane for a few minutes after engine shutdown to observe the indications as the gyros spool down. This is disconcerting and distracting when you are actually flying, trying to control the airplane. Your task will be a lot easier if you cover up the inoperative instruments. The fact that electrical or pump failure makes the gyroscopic instruments vulnerable to failure stresses the need to include the other instruments in the scan. Any discrepancy between the gyro instruments and the other instruments must be viewed with suspicion. The best evidence of a pump failure is when the other instruments do not confirm what is shown by the heading or attitude indicators. When a failure happens in instrument conditions, ask ATC for help. The most desirable response from ATC is clearance and vectors to VFR conditions. If this is not possible, ask ATC to avoid altitude changes, delays, and course changes. If plans change while you are en route, let the controller know as far in advance as possible. If the change in plan is because of an emergency, be clear about this. If it's a condition that calls for any special handling or priority over other traffic, use the E word and declare an emergency. Be specific about any special assistance you think you'll need, such as vectors and a no-gyro approach following the failure of an instrument or a system that powers the instruments. If you do a poor job of fuel planning and are arriving without the legal required fuel, advise the controller of a minimum fuel status. This does not constitute an emergency, but is an advisory that an emergency is possible if there is undue delay. There is no priority handling of minimum fuel aircraft. If you are up to your ears in alligators but not fuel, and the outcome will be in doubt if you do anything other than be first in line, emergency is the magic word.
The one thing that can't be stressed too much is that controllers do respect the responsibility placed upon pilots. In return, they expect pilots to live up to that responsibility. Probably the toughest position for a controller is when he recognizes that a pilot is trying to shift some of that responsibility to the ground. A controller can, for a fact, declare an emergency for a pilot if the controller feels the situation is getting out of hand and the pilot is not acting. By so doing, the controller can then give priority and issue clearances that will get the airplane on the ground as soon as possible. The pilot still has to fly the airplane, though, and his having abdicated other responsibilities might make the controller question the pilot's ability, right up to the point where the airplane is safely parked on the ramp.
FAR 91.185 defines on less than one page the actions we pilots should take in the event of a two-way radio communications failure. The AIM expands on these rules with the opening statement that it is virtually impossible to provide regulations and procedures applicable to all possible situations associated with two-way radio communications failure. When confronted with a situation not covered in the regulation, we pilots are expected to exercise good judgment. The AIM further states that pilots should not be reluctant to exercise the emergency authority that allows the pilot to deviate from the rules to the extent necessary to cope with the emergency. While the rules for pilots are relatively simple and do not cover all potential situations, the ATC system has many procedures to follow. In a situation not directly covered by the rules, ATC clears the airspace for all possible actions the pilot may take. The first rule is really common sense. If the failure occurs in VFR conditions, or if VFR is encountered, the pilot should continue under VFR, land as soon as practicable, and call ATC on the phone. If the failure happens in IFR conditions, or it's not possible to remain VFR, the rules cover each dimension of control. When confronted with a situation, it's best to consider each of the dimensions of control, route, altitude, and time, separately. For route, follow the last clearance. If the last clearance is short of the destination, follow the route that ATC has advised may be expected. Absent a last clearance or expect further route, follow the route filed on the flight plan. If being radar vectored, ATC expects the pilot to fly direct from the point of failure to the fix, route, or airway specified in the radar vector clearance. While route has a definite order of priority, altitude is based on flying each airway segment at the highest of 3 possible altitudes. Airway segment, as it's used, means a portion of an airway that has an altitude prescribed. During the cruise portion of the flight, fly at the highest of the following altitudes or flight levels: the last clearance, the minimum altitude or flight level for IFR, or the altitude or flight level specified in an expect further clearance. En route to Salt Lake City on Victor 484, a pilot has a two-way communications failure approaching the Twin Falls Vortac. The last assigned altitude was 9,000 feet, and the pilot was not given an expect further clearance. From Twin Falls to Woden, the last assigned altitude, 9,000 feet, is higher than the minimum for IFR. From Woden to Dryad, the minimum for IFR, 12,000 feet, is higher than the last clearance. The segment to Dryad should be flown at 12,000 feet. FAR 91.177 specifies that except for a minimum crossing altitude, climb to a higher minimum altitude shall begin immediately after passing the point beyond which the higher altitude applies. At Dryad, the minimum crossing altitude of 13,000 feet is the minimum for IFR. A climb from 12,000 to 13,000 feet should begin when necessary to reach 13,000 feet before passing Dryad. After passing Dryad, climb should continue to 16,000, the minimum for IFR on the segment to Switz. Between Switz and Cause, the minimum for IFR, 11,500 feet, is higher than the last clearance altitude of 9,000 feet. After passing Switz, a descent to 11,500 feet should be made. From Cause to the Salt Lake City Vortac, 9,000 feet, the last assigned altitude, is the higher altitude. After Cause, descend and fly to the Vortac at 9,000 feet. Descent for the approach can start at the initial approach fix, or the fix from which the approach begins, and as close as possible to the estimated time of arrival. Descent from the last en route altitude cannot start until both conditions are met. Which approach to use? Which initial approach fix to use? An important part of all communications is the pilot's acknowledgement of receipt of a communications clearance. If the pilot has acknowledged receipt of the information about the approach and initial approach fix to use, the pilot must use that approach and initial approach fix.
If receipt of this information has not been acknowledged, ATC will clear all the approaches and initial approach fixes.
ATC controls time by having aircraft hold. An important part of a holding clearance is the expect further clearance time. If a communications failure happens while in a holding pattern, leave the holding fix at the expect further clearance time. This is true whether holding en route or for an approach. The transponder code for a two-way communications failure is 7600. By replacing your current code with 7600, you alert ATC to the loss of communications. This squawk shows up on the controller's screen as radio failure in your data block. Don't make the assumption the controller sees you right away. It's possible your airplane may not be in radar coverage. Generator or alternator failure will eventually cause failure of all electrical systems. This means loss of all NAVCOM radios. The instruments which monitor the condition of the charging system, ammeter, voltmeter, load meter, or warning light, are as important as the flight instruments. If the generator or alternator failure is caught early, there are a lot of things the pilot can do. Unnecessary electrical load can be turned off. ATC can be informed of the problem, and an approach and landing can be made at the nearest suitable airport. There are many options available while there is enough battery power to communicate. The list of options shortens dramatically when there isn't enough battery power to transmit. Complete radio failure is one of the reasons why the complete IFR weather briefing should answer the question, where is the closest VFR weather? That might be above or below. It might be in front or behind, off to the left or off to the right. The answer to that question may never be needed, but it's an inexpensive insurance policy. With a total NAVCOM failure, the best possible solution is to fly to VFR conditions.
Thanks for flying along with us as we've explored some of the facets of instrument flying, an activity that is extremely challenging as well as extremely rewarding. Fly safely.